So, we are going to switch language in the course. I'm going to try to speak slowly so that people who are not very familiar with English can follow. But several students asked if it would be possible to switch to English because they don't speak Portuguese. And besides that, all the Portuguese-speaking students said it would be okay. So let us try to have a few classes in English and see how this goes. I'll try to speak slowly and write as much as possible on the board to make it easier to understand. So in this class, we're going to talk about martingales. It's going to be an introduction to martingales. So martingales is a very interesting and rich subject in probability. It's also related to the Brownian motion and to random walks that we have talked earlier. So martingales, the name martingale comes from a game, a betting game that has been analyzed by probabilists, but the term now is much more general. It's not only about this specific betting game, but martingales is very related to the idea of games. It gives a notion of what is a fair betting system somehow. So we're going slowly to that. But one important observation is that bets are very connected to information. Right? If you know what are going to be the next numbers in the lottery, you would just bet on those numbers and be rich. So the fact that you don't know the information is what makes the game interesting to start with. And we have a problem. We have to define information a bit better, right? What is information, mathematically speaking? And there is one subject that has been studied in Probability I, which is conditional expectations. Which is an excellent tool to model information. So I don't know if conditional expectations has been presented to you as a tool to model information, but that's essentially the main application of conditional expectations. So let's talk a little bit more about this. So let's recap a bit the subject. So if x is a random variable, and x belongs to L1, what does that mean? That the expectation of the absolute value of x is finite. That's the precise meaning of this. Then we also fix, so where is this random variable defined? In some probability space with some probability p. And let's suppose that we have a sigma algebra F, or sigma field, sometimes called in English, that is a sub-sigma field of the original one. So the intuition behind this is that F has less information than A. And we're going to describe this several times in the course. So I hope that after a few lectures, this imprecise statement will be intuitive for everyone. So we have a sub-sigma field of A. We are trying to give this intuition that F has less information than A. And we say that a random variable y is the conditional expectation of x given f if a few things happen. So first, y should be f measurable. So y is not only a random variable. This means that y belongs to A, but actually y should belong to f. Y should be measurable with respect to the smaller sigma algebra, which is harder than this, by the way. And 2, for every A in f, the expectation of x at A should be equal to the expectation of y at A. So these are the two statements that are required for y to be called a conditional expectation of f of x given f. And we know several properties about this. So recapitulation. So 1, such a thing exists. So if you have x in L1 and a subsigma field f, then there exists a random variable. This is actually the name we give to the random variable, right? Such that it's f measurable and this property holds. 2, this is almost surely unique. So there could be 2 solutions to this, but they will be equal to one another with probability 1. So another property that is proved in probability 1 is suppose that z is already f measurable, then the expectation of z given f is going to be just z. Right? It already satisfies this, and this is going to be trivial, so good. Whenever I write this, you have to remember that this is an almost sure statement. This can be generalized. Suppose that z belongs to f, and z times x is still L1. So the product still has a finite expectation in absolute value. Then the expectation of the product is going to satisfy this. So an intuitive way to think is z will leave the expectation. It can get in and get out for free if it's in f. 5, and last property, if x is independent of f, then the expectation of x given f is just the expectation of x. So let's recall what this means, right? We know what it means to have 2 independent events. This is probability of AB is probability of A, probability of B. If we say that x is independent of y, now, before that, if we take a family of events A and a family of events B, the independence means that A is independent of B for every A in A and B in B. So this is what it means for two families to be independent. And now, what does it mean for X to be independent of Y? This is the sigma algebra generated by X is independent of the sigma algebra generated by Y. And finally, what's X independent of a family? This is the sigma algebra generated by X is independent of the family. So everything is very intuitive, but you have to remember there are several definitions. And here we are asking that the sigma algebra generated by X is independent of this family, then the conditional expectation is just the expectation. Okay, this is just what you probably have seen already in Probability I. There are other things like there are analogous results. Things that we know are true for expectation are also true for the conditional expectation. So the conditional expectation is linear. So the conditional expectation of the sum is the sum of the conditional expectations. Jensen's inequality is true for the expectation and for the conditional expectation. The dominated convergence theorem is true for expectation and for the conditional expectation. The monotone convergence theorem is true for expectation and conditional expectation, and so on. So there are several results that translate from here to here. Okay. So now let's go back to the definition a little bit. And let us give a bit more of an intuition of why F can be understood as a measurement of information. So when we have a state space omega, usually what we think is something will happen, and this something is some element of omega is going to be chosen at random. So this is what a state space and a sample should be understood intuitively. In the end, we are never doing this. We are just defining omega, sigma algebra, and probability, and doing calculations. But the intuition is that this probability will pick a point here at random with some properties. Okay, now imagine that the sigma algebra F is the empty set omega, a set A and A complement. This is a sigma algebra that looks more or less like this. This is A, this is A complement, and that's essentially the sigma algebra generated by A. Okay? So again, this sigma algebra has nothing to do with our original sigma algebra. Anyway, we are still going to pick a point here at random, omega, right? So why we understand this as a measurement of information? The way we should understand this is the following. If we know the sigma algebra F, means that we know for every A in F, if the sample point belongs to A or not. So if we know this sigma algebra, we know if X is in this group or in this group, sorry, omega. We know that omega fell here or here. But we don't know if it was this omega or this omega. We have no way to distinguish what happens inside one of these sets. So for example, suppose we are on R2 with the Borel sigma algebra. So this is the complete sigma algebra. It's all the information. But on R2, there are two very natural functions. The function x that takes 2 points and return the first one, and the function y that takes 2 points and return the second one. So this is x, the projection, and this is y. So the sigma algebra generated by x is given by A times R, where A is any Borelian set of R. So this is a typical measurable set in this sigma algebra. It's a cylinder. So if we know this sigma algebra, that's like saying we know x. We know the projection, but we don't know if the sample point was this one or this one. Okay? If they have the same x coordinate, we don't know, we can't distinguish them if we only know the sigma algebra. So that's the intuition behind knowing a sigma algebra. Okay, so why is this important? Because we are going to define what a martingale is, and after we're going to define what a Markov process is, and all these definitions have some notion of information in it. So forget Markov process for now. A martingale is a game that is honest given your information. So if all you know is this, then you're doing the best you can do, somehow. So we have to use this notion of information to define a martingale, and we have to use conditional expectations. Okay, so before we have to recall, we are going to define so a martingale is going to be a family of random variables indexed by n. So you can think of it as time n, and this is a family that is indexed by time. So for every n, x n is a random variable. Okay? And we also need to introduce a family of sigma algebras. So this is going to be a family of sigma algebras, and this is called a filtration if for every n, let's put a 0 here, it's actually better. It's like the programming language that have n starting at 0 or 1. Usually this is better. So for every n, fn is contained in fn plus 1. So this is what a filtration is, means. And the intuition behind is as time progresses, so time 0, 1, 2, 3, you get more and more information. That's why they say with age comes wisdom, right? Because as time progresses, you get more and more information. So this is what a filtration is. We say that xn is adapted with respect to a filtration simply if xn belongs to fn for every n. So this is a simple definition. We're just saying that a process like this is adapted if the information you have until time n is enough to determine xn. So now we have all the setup to define a martingale. But let's just give an example before. So suppose that you already have the family of random variables like this, any family of random variables. If you define fn to be the sigma algebra generated by x0, x1 until xn, then xn is adapted to fn, which, by the way, is a filtration. So that's what we call the canonical filtration. So if you don't have a filtration in mind, like there's no obvious filtration, this is the obvious filtration. There is a process you are interested in. You just take the sigma algebra that observes this process. Then this is going to only grow, right? This is going to be bigger as you add more variables. So it's going to be a filtration. And of course, xn belongs to this sigma algebra. So it's adapted. So this is the canonical filtration. But it's very important that we can use filtrations that are not canonical. Sometimes, for example, we have one process and another process. So now there are two canonical ones. So we have to distinguish, like, oh, we are using the filtration, the canonical filtration of x, or the canonical filtration of the pair. So now both are adapted. So it's important that we have the freedom to choose the filtration, not always the canonical. Okay. Finally, we can define a martingale. So if we have xn, a family of random variables, if we have fn, a filtration, then the family xn of random variables is called a martingale with respect to this filtration. So it's never, a family is never a martingale, period. It's always a martingale when you look through the lenses of this filtration. So martingale with respect to this filtration, if three things happen. So first, xn should have finite first moment. In other words, xn should always belong to L1. Okay, this is something people forget several times. Don't forget, the variables should be integrable. The second property, xn, should be adapted to fn. In other words, xn should belong to fn for every n. So this is also something people forget. And it's natural that people forget, because this is just the setup. The most important property is this one. Don't forget these two, but this is the most important one. For every n, the conditional expectation of x, n plus 1. So because of 1, this makes sense. Given fn is just xn. So this is the definition of a martingale. Now, I think I can spend some time giving an intuition of this. Why is this related to games, and what's the notion of fair here? So let's go slowly. We are playing a game. xn is going to be the amount of money we have at time n. So this is the intuition. As the game goes, the amount of money we have is xn. So at time 0, we have x0 money. At time 1, we have x1. At time 2, we have x2. So this is how our money evolves. And clearly, our money is random. There is some random thing that determines how much money we have at each time. So this is the information we have as we see the game progress. So of course we need that at time n we can see how much money we have. That's a very intuitive requirement. But maybe we can see other things. We can see how much money other people have. Maybe we can see if it's raining or not. So there could be a lot of information here that we gather until time n. But it's important that we know how much money we have at time n. It's a technical requirement that our money is always in L1, because otherwise we can't talk about this. Now this is the heart of the definition. What it's saying is, if I only know what's happening until time n, so let's say someone enters the room, sees the game from time 0 until time n. They see all the sigma algebra fn. Now they're trying to guess how much money I'm going to have in the next round, so in the future. So they don't know. This is random, and it's not measurable with respect to fn necessarily. So there is some randomness here. You don't know how much money I'm going to have in the next turn. But you can calculate the conditional expectation. This is how much money you expect me to have. And the fairness of the game is that the amount of money I expect to have in the next round, given the information I have now, is just the amount of money I have now. So I don't expect to lose or to win money in the next round on average. Of course I can lose money. xn could be bigger than xn plus 1 or smaller than xn plus 1. I can lose or win money, but not in average. So I think this is the intuition, but we have to give concrete examples to understand better what's going on. So first example, imagine that we have a family of random variables that are IID and in L1. Okay? And we define xn to be xi0 plus xi1 until xin. So this is, again, a random walk. So now, is this a martingale? First, the intuition. We have to say what Fn is to ask if something is a martingale. So Fn is going to be the canonical filtration, meaning Fn is the sigma algebra generated by the Xn. Okay, so we have a candidate. Is this a martingale? Okay, if I have this amount of money, in the next round, I'm going to have this plus xn plus 1. So I don't know, maybe this expectation is going up or down. Depends on the expectation of xi1. Because this is the expectation of every psi. Let's assume for now that this is 0. Then I don't expect to gain or lose money on average in the next round. So let's see if all the requirements are fulfilled. So the expectation, so the fact that xi belongs to L1 implies that xn belongs to L1 for every n. So L1 is a vector space. So xn belongs to Fn because it's the canonical filtration. Now the heart of the definition, what's the expectation of xn plus 1 given Fn? So let's break this down. I could write this as a long sum, but I don't want to do this. I'm just going to write xn, because we want to get xn in the end, and separate the last term. Okay, conditional expectations are linear. So I can write it like this. Now, let us observe that xn is measurable with respect to Fn. So this first term is just xn. Remember that things that are measurable can go out of this expectation. So this is what we said about z a bit earlier. Now here, Fn is the canonical filtration. But it's contained, it's actually equal to the sigma algebra generated by xi0 until xin. So this is the sigma algebra generated by the first n variables. But this family is IID. So the n plus 1 is independent of the previous ones. And we know that if the expectation, the conditional expectation of something independent of the sigma algebra is just the expectation. So this is the expectation of psi n plus 1, which is 0. So we just verified that the amount of money I expect to have at time n plus 1, given what I know now, is what I have now. So this is a martingale. And this is perhaps the most important example of martingales, although the next example I'm going to give is also extremely important. So, but before I give another example, let us make a slight modification in our definition to generalize it a little bit. So let's go back to the definition of a martingale. And we assumed that the game is fair, right? But the game could be consistently unfair. That's also an interesting scenario, right? So we call a game a super martingale if the same thing is true. The variables are in L1, they're adapted, but the expectation of what you have in the future is smaller or equal than what you have in the present. So this is a sad and unfair game, but it's a useful definition. And we call something a sub-martingale if it's consistently better. So this is a slight generalization of the definition that helps us understand unfair games or super fair games. Now, people forget which direction is which. Like, is super martingale this sign, or this sign is sub martingale this sign? So there's a trick that I use, I never forget. And the trick is, think that the definitions, the names, were chosen by a casino. So if you are the owner of a casino, of course you're going to make an unfair game for everyone. You want people to have less money in the future than they have in the present. You want things to go down for the players. But you don't want to tell this to anyone or to let this be very obvious. So you call this a super martingale because it's a marketing scheme. So say it's super game where everyone loses. I don't know, this works for me. The original names, super martingale and sub martingale, are not chosen by a casino. They come very naturally when you see that martingales appear when you study diffusions on harmonic functions. So it's something that, it's one of the main importances of martingales. And in that context, if you use a harmonic function, you get a martingale. If you use a superharmonic function, you get a super martingale. If you use a subharmonic function, you get a submartingale. So if you're very good in analysis and you remember if a superharmonic function uses this sign or this sign, then you don't need to remember the casino trick. I don't. Actually, I remember what a superharmonic function is by remembering the casino. So, okay. We have an example here that is fair. But if the expectation of psi I would be smaller or equal than 0, now we are losing money potentially in every turn. Then this expectation is going to be this expectation, which is smaller or equal than this. So it's a super martingale. Again, in the same example, this would be a sub martingale. So just generalizing the example to include a super and a sub martingale. Now let's give a second example, which I think is as important as this one. It's going to appear several times. It's the most silly example of all. It's actually simpler than this, but it's very important. So suppose that you have just one random variable in L1, and Fn is a filtration. Okay, so how do you obtain a martingale from this? It's very simple. You define xn to be the sigma algebra, sorry, the conditional expectation of x given the sigma algebra Fn. So this, what's the intuition of this? Somehow x is how much money you have when the game finishes, like time equals infinity or something like this. Suppose that when the time is infinite, you still have some amount of money which is in L1. Then this is how much time you have in n. It's just the amount of money you have in the infinite future conditioned on the information you have until time n. So this shows that it's actually very natural to see martingales everywhere. So what the objective of this part of the course is to prove several results about martingales. So we're going to see conditions under which martingales converge, what are the moments of the martingale, things like this. So there will be several beautiful results about martingales. But in order to apply, we expect martingales to appear in nature, right? And this is a natural way in which martingales appear. Just take what will happen and look at the information you have. This is a martingale. So what is the proof that this is a martingale? So first, the conditional expectation belongs to L1. This is proven in Prob 1. So I'm not going to give a proof. If a variable is in L1, the conditional expectation is also in L1. Clearly, Xn belongs to Fn. That's part of the definition of being a conditional expectation. Now, the most important thing to test. What's the expectation of Xn plus 1 given Fn? So this is the expectation of x given Fn plus 1 given Fn. And if you remember from probability 1 again, there is a property called the tower property of the conditional expectation. If you're taking conditional expectations of conditional expectations, in the end, you only have one of them. So if this is contained in this, or this is contained in this, so you need one inclusion, what will survive is the smallest sigma algebra. So in this case, the smallest sigma algebra is this. So that's the tower property. If this is contained in this or this is contained in this, you can remove the biggest sigma algebra. And this is the definition of Xn. So again, we checked that this is a martingale. A nice property of a martingale concerns its expectation. So suppose Xn is a martingale. So the expectation of Xn is the expectation of the conditional expectation of Xn given, Xn minus 1, given Fn minus 1, right? We know that this random variable is equal to Xn minus 1 almost surely. So if they are equal almost surely, the expectation is the same. And you can continue this until expectation of x0. So the expectation of a martingale never changes. The amount of money you have is constant in expectation. Now, if you're talking about a super martingale, then this is still true. But now this random variable is smaller than this. And you can continue with this until you get that the expectation is only decreasing. If it's a sub-martingale, the inequalities will switch, and your expectation is only increasing. So I think this ends the introduction to martingale. We're going to make shorter videos now, not 1.5 hour lectures. So this is the introduction to martingale video, and we are going to start the next video talking about more profound properties of martingales.